Remember today's goal of this lecture. Today I will say some questions of sequence of functions just as a review. Just as a review, today I will indicate some questions of sequence of functions. Okay? Just as a review, actually today's goal just as a review. This is today's goal of this lecture. First, I will say some question of Dennis theorem. We all of us know Dennis theorem. In my previous video, in the playlist, only there are one separate video about Dennis theorem. Today, I will see just some example. Today I have collaborate some example just as a review. Only I will see some example. Okay, this is today's goal of this lecture. Just as a review, at first see what is the statement of Dennis theorem. Statement of Dennis or Dennis theorem is let D be compact subset on R. That means here the domain is always compact and the sequence of function defined on D to R be a sequence of function on D that converges pointwise to the function f. If the sequence of function fn be monotone sequence on the set D, then we can tell this sequence of function converges uniformly. That means here the domain always would be compact. Fn, sequence of function fn converges always f pointwise, and always sequence of function would be continuous. If this sequence of function be monotone, that means either monotone increasing or monotone decreasing, then we can tell this convergence of sequence of function fn converges to f. This convergence is uniform convergence. Uniformly convergence. I hope my all viewers have understood this is okay. Let's see some example. First question. So that fn x equal to x over n plus x square converges uniformly on 0, 1. Obviously, this function fn x converges to 0 pointwise. And here the domain is closed interval 0, 1. So we can apply Dennis theorem. And notice here the graph of the sequence of function, this is f1 x over 1 plus x square, f2 is x over 2 plus x square, f3 is x over 3 plus x square, f4 x over 4 plus x square, so on. This is be the monotone decreasing function. So second condition of Dennis theorem has satisfied monotone. And the sequence of function here be the continuous, obviously. So we can tell by Dennis theorem fn converges to 0 uniformly. I hope my all viewers have understood. Second, fn x equal to tan inverse nx on closed interval 0, 1. Notice here the domain is closed interval 0, 1. But at first thing, can I apply Dennis theorem? Notice, when x equal to 0, fn converges to 0 because tan inverse 0 equal to 0. But we all of us know limit n tends to infinity, tan inverse x always goes to pi over 2. That means when 0 less than x less than equal to 1, then this value would be pi over 2. So fx pointwise converges to 0 and pi over 2. So fx not be continuous function. So since fx not continuous, so we cannot apply Dini's theorem. We all of us know when f be continuous, then we can apply first condition of uniform convergence. But here f not be continuous. So we can tell f not be uniform continuous on the closed interval 0, 1. But if we apply interval a1 where a greater than 0, then this is uniform convergence. Because here the continuity break only at the point 0. So if we consider the interval closed interval a1 where a greater than 0, then tan inverse nx is uniformly converges on this interval, because notice f1 is tan inverse x, f2 is tan inverse 2x, f3 is tan inverse 3x, f4 is tan inverse 4x, so on. And here the sequence of function be monotone decreasing function. So this sequence of function, since the domain is closed and bounded compact, and sequence of function every function be continuous, so we can tell this sequence of function is converges uniformly on the interval closed interval a1 where a greater than 0. Next, when x to the power n on the interval 0 half, then is the sequence of function converges uniformly, because on the interval 0 half x to the power n goes to 0. But if we consider 0, 1, then at the point x equal to 1, x to the power n goes to 1. So if we apply this interval, then this sequence of function does not converges uniformly. But if we consider this interval 0 half, then always by Dini's theorem we can tell this sequence of function converges uniformly, because notice the graph, this is f1, sorry, this is f2 x squared, this is f3 x cube, this is f4 x to the power 4. Obviously the sequence of function converges pointwise to 0, and this is the monotone decreasing sequence of function. So and every function be the f1, f2, f3 all are continuous. So by Dini's theorem we can tell fn converges uniformly to the function f on 0 half. This is only true on this interval, not this interval. Similarly, if we consider x to the power 1 over n, we all of us know x to the power 1 over n, if we consider this interval, when lies open interval 0 to less than equal to 1, then this value always 1. But when x equal to 0, then this value equal to 0. So if we consider x close interval 0, 1, then this is not convergent, not uniformly convergent. But if we consider x to the power 1 over n on this interval closed a open closed a to 1, where a lies between 0 to less than equal to 1, then we can tell obviously this sequence of function be uniformly convergent by similar to before by Dini's theorem. Similarly, x to the power n times 1 over 1 minus x, this is converges uniformly on this interval by Dini's theorem, because notice obviously this function fn converges to 0 on the interval close 0, 1. Here the domain is compact, and notice this is the F1, this is F2, this is F3, this is F4. That means here the sequence is monotone decreasing sequence, and all F1, F2, F3, F4 so on, all are continuous. So we can tell Fn converges to 0 not pointwise. This is uniformly on the closed interval 0, 1 by Dini's theorem. I hope my all viewers have understood this type of theorem. By Dini's theorem, if you know the Dini's theorem, and you can tell is this sequence of function uniformly convergent or not by easily. Because I hope my all viewers have understood this theorem, Dini's theorem, is the easiest way from MN test. If you know the Dini's theorem, then you can just construct any sequence of function be uniformly convergent or not very easily. Same type of example we can evaluate by MN test. This function is uniformly continuous, but I hope my all viewers have understood. Dini's theorem is more easiest way. Okay. Next I will see some example which had come in different type of competitive exam. Next example which had come session net 2019 exam. The question is, let gnx equal to nx over 1 plus n square x square, where x belongs to close 0 open infinity. Which of the following is true as n tends to infinity? Option 1, gn goes to 0 pointwise but not uniformly. Option 2, gn goes to 0 uniformly. Option 3, gn goes to x for x belongs to close 0 open infinity. And option 4, gn goes to x over 1 plus x square. Notice when x equal to 0, then gnx equal to 0, and when x not equal to 0, notice this is the infinity by infinity. So limit n goes to infinity, nx over 1 plus n square x square means, since this is the infinity by infinity, so we can apply here the L Hospital rules. This value is n over 1 plus 2n square x, and as n goes to infinity, limit n goes to infinity, this value is equal to 0. So this value is equal to 0 when x not equal to 0 also. So gn actually goes to 0 pointwise. That means gn goes to x, gn goes to x plus 1 plus x square. This is be the wrong option. Now I will see, is this option, is this convergence is uniform convergence? For this, at first I will use subsequential test. What is this test? We all of us know, if we find one sequence xnk such that absolute value of gxnk minus gxn, gnxnk minus gnxnk, if this absolute value does not goes to 0, then we can tell this convergence is not uniform. For this, if we consider one subsequence xn equal to 1 over n, then limit n goes to infinity, g xn k means here n over n times 1 over n divided by 1 plus n square times 1 over n square. Here g xn k means g means here this value 0. So this value equal to 1 over 2, which is not equal to 0. Therefore, by this sequence test, we can tell this convergence is not uniform. Also, so you can apply here Mn test, and by Mn test you will see similarly this is not uniform convergence. And Mn equal to supremum x belongs to closed 0 infinity nx over 1 plus n square x square. Consider this value equal to y, and we all of us know at critical point the function has a maximum or minimum value, and the definition of critical point means y dash equal to 0. That means all the points where y dash equal to 0, and all those points where y dash tends to infinity, then the function has a either maximum or minimum. Here y dash equal to would be such type of always the denominator part would be 1 over n plus n square x square to the power whole square, and critical point means either y dash equal to 0 and y dash tends to 0, and here would be other part also. Y dash tends to infinity when this part would be 0. That means 1 plus n square x square equal to 0. That imply x equal to 1 over n. At this point the function has a critical point, and at x equal to 1 over n, at this point the function has a maximum value. And we all of us know if Mn goes to 0, the convergence is uniform. But at the point x equal to 1 over n, this value n times 1 over n over 1 plus n square times 1 over n square, and this value is half. That means limit n tends to infinity Mn does not converges to 0. Okay? Therefore, Gn converges to 0 pointwise but not uniform. So option 1 is a right option. Next question, this is also very important. Let fn be sequence of function which is defined on closed interval 0, 1 by fn x equal to x to the power n log 1 plus square root of x over 2. Then which of the following statement are true? Option 1, fn converges pointwise on the closed interval 0, 1. Option 2, fn converges uniformly on compact subset of closed intervals 0, 1, but not on the closed interval 0, open interval 1. Option 3, fn converges uniformly on closed 0, 1 but not on closed 0, 1. Option 4, fn converges uniformly on closed interval 0, 1. Notice here fn x equal to x to the power n 1 log 1 plus square root of x over 2. When x equal to 0, then fn x equal to 0. When x equal to 1, then this is 1 and this is log 1 plus 1 over 2, that means 2 over 2, that means log 1, and log 1 always 0. And when x lies between 0 to 1, then this value is, when x lies between open interval 0 to 1, then this value goes to 0, then the function fnx also goes to 0. So actually fnx converges pointwise to the function fx equal to 0 function. That means fn converges pointwise on close interval 0, 1. Now I will see, is this convergence is uniform convergence? For this I will use the Mn test. Mn equal to supremum x belongs to close interval 0, 1 x to the power n log 1 plus square root of x over 2. When x equal to 0, then this value is equal to 0. When x equal to 1, then Mn also equal to 0, and when x lies between 0 to 1, then if we consider supremum exists at this point n over 1 plus n or 1 minus 1 over n, then actually you can consider this is y, then you can find y dash, but this method is very critical method because here the derivative part would be long. So for shortcut trick, if you consider x equal to, if we consider the supremum value exists at this point when x lies between in this interval, then Mn would be 1 over 1 plus 1 over n to the power n log 1 plus square root of 1 over 1 plus 1 over n divided by 2. And as n goes to infinity, we all of us know this value goes to 1 over e, and this value goes to, as n approaches to infinity, this value goes to 0. Here log 1 plus 1 over 2, this value log 2 over 2 means 1, that means this value 1, and we all of us know this value equal to 0. That means as n goes to infinity, this value tends to 1 over e times 0, this value equal to 0. So Mn goes to 0 at each point when x equal to 0, at x equal to 1, or when x lies between open interval 0 to 1. So since supremum of these values tends to 0, that means this convergence is uniform convergence on close interval 0, 1. That means option 4 actually right option. Fn converges uniformly on the close interval 0, 1. So obviously Fn converges pointwise. In the question, second option, not uniform on close interval 0, 1. For this option 2 is right. Wrong. Option 3 also wrong, because Fn converges uniformly but not on close interval 0, 1. For this is also wrong. Only option 1 and option 4 is a right option. I hope my all viewers have understood this question easily. Okay, OA. Fnx equal to 1 over n square x square. This is true for all n belongs to natural number. Then which of the following statement are true? Option 1, Fn converges pointwise on the close interval 0, 1 to a continuous function. Option 2, Fn converges uniformly on closed interval 0, 1. Option 3, Fn converges uniformly on the closed interval up to 1. Option 4, limit n tends to infinity, integration 0 to 1 fn x dx equal to integration 0 to 1 limit n tends to infinity fn x dx. Which of the following statements are true? Here notice fn x equal to 1 over 1 plus n square x square, where n belongs to natural number and x belongs to R. Is fn converges on closed interval 0, 1? Notice fn x equal to 1 when x equal to 0 and 0 when x not equal to 0, because limit n tends to infinity, this value fn x tends to 0. So when x not equal to 0, then function goes to 0. That means option 1, fn converges pointwise on closed interval 0, 1 to a continuous function. This is be the wrong option, because notice here fn converges 1 and 0. So this is converges to discontinuous function. So option 1 is a wrong option. Since fn converges to discontinuous, pointwise converges to discontinuous function, so sequence of function uniformly convergence on closed interval 0, 1, this would be wrong. Next, fn converges uniformly on the closed interval half 1. Notice in the interval half 1, the fn converges to 0 when x belongs to half 1. That means fn converges to continuous function. Okay. Now we have to prove is this convergence is uniform. For this, consider mn equal to supremum of closed interval up to 1, 1 over 1 plus n square x square. Notice, we all of us know, in this interval, if you see the graph, this is the monotone decreasing sequence. Since the monotone decreasing sequence, so since fn x is monotone decreasing, so supremum value exists at the point half. So this value mn would be, if we put the value half, this value would be 1 plus n square times 1 over 4. So this value would be 4 over 4 plus n square, and as n goes to infinity, this value tends to 0. So since mn tends to 0, so by mn test we can tell this sequence of function converges uniformly on the closed interval half to 1. Next question, limit, is this integration value exist? If there are intervals 0 to half, then where since the function is uniform, 1 to half, 1 to half, half to 1, half to 1, then by uniform, since the sequence of function is uniform converges on this interval, so we can tell this option always true. But since here the interval, given interval 0 to 1, so this is may or may not be true. For this we have to check. Here integration 0 to 1 fx dx, this value is equal to 0. But if we apply integration 0 to 1 fn x dx, this value would be 1 over 1 plus n squared x squared dx. So this value would be tan inverse nx over n. Here the integration 0 to 1. So this value equal to tan inverse n over n. So if we apply here, since we have to find limit n tends to infinity, this is the infinity by infinity. So if we apply the L Hospital rule, this would be 1 over n, and this is 1, and this value equal to 0. That means this integration part is equal, but the sequence of function not uniform convergent. I hope my all viewers have understood. When sequence of function be uniform convergent, then this integration on this interval, integration always be interchange. But sequence of function when not be uniform convergent, then this interchange of integration may or may not be true. Here this is true. Okay. Today I will stop here, but at first I will highly recommend you, please see today's video with pay attention, because to check uniform convergence, Dini's theorem is actually very important, and all other question also very important for any competitive exam. So at first I will highly recommend you, please see today's video with pay attention. And if you don't see my previous video of sequence of function, then see my playlist. If you don't see my previous video of sequence of function, then today's video would not be clear easily. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.